Hi everyone. So in the last video we went over a form of complex ANOVAs called nested ANOVAs. And right now we're going to go over the second type of complex ANOVA that you can have, which is a crossed or factorial ANOVA. And so this goes along on the same functions as far as categorical and numerical variables. So we're first going to set up our working directory. That always needs to be done. And I apologize if at any point you hear like a slight snoring sound in the background. My cat Figaro is sleeping on the futon right next to me, and he likes to snore a lot. It's ridiculously adorable. Okay, so the data set that we're working with is this spruce data set. And it was an experiment that was set up to test the hypothesis that healthy spruce seedlings break buds sooner than disease spruce seedlings. So the study design itself represents a crossed ANOVA. Now for this, you definitely need the CAR package, so install that now. Oh, shush. So install that now if you don't have it. And again, you can install the package by going to the packages area, clicking install, typing in CAR, clicking that, and then install. I already have mine, R just yelled at me, so all I have to do is pull up the library CAR. All right, so let's look at our data set. Get some of the summary statistics. All right, so there were two crossed factors, pH, which is acidity, and there was 3 levels. You had 3, 5.5, and 7, and health, and that was measured at 2 levels. You had either healthy or diseased. And then the response variable was the average from 5 buds, bud emergence rating, which is called B rating, so bud rating, on each seedling. And the sample size itself varied for each combination of pH and health. I think something from like 7 to 20 or 25, something between there. So since you have a crossed ANOVA, there are 3 null hypotheses. The first is the null hypothesis that there's no effect of pH. The second is that there's no effect of health. And the third is that there's no effect of interaction between pH and health. So that's what crossed ANOVAs deal with. They deal with an interaction term. So before we proceed, we have to make sure that all of our variables are being treated by R correctly. And I can see already from the summary statistics that they are not. We can test again by pulling up the string. And so we see that acidity and health, we both want to be factors. And right now, R is treating health as an integer and acidity as a numerical variable. So we need to change that. And also, group is being treated as an integer, which we don't want. So we're going to tell R, or coerce it, into coding these as factors. So we're going to use the as factor function. So then we can make sure that the factors, that those variables were changed to factors, which they were here. So that's good. And we can, again, check that in the summary statistics. So you see that you have, these are the factors, factor ratings, basically, or factor ranges. Okay. So before we can build the model, we need to check assumptions. And there are 2 assumptions for crossed ANOVAs. First is normality, and the second is homogeneity of variance. So we're going to take a look at the box plots and use these as visual tests for normality, plotting the response variable, which is your bratting or B rating, by group. So we're going to separate it out per group. So run that. So most of the plots, here's our box plot thing over here. So most of the plots seem all right, though none appear to be really normally distributed. However, you have like a slight skew in their distribution, but it doesn't seem to be significant. There's one plot right here, number 3, that has outliers. So you have 3 that are situated at the high end, the extreme high end, and then one that's situated here at the extreme low end. But again, it doesn't, the skews don't look to be anything significant. So we're going to run with it. And we're going to check the residuals and verify that they're also normally distributed. So I'm going to make a residual plot, which basically plots the residuals against the group means, which are your predicted variables or your estimates. And so this is the model that we get. Now, in order to interpret this, you would interpret it the same way from the nested ANOVAs. You look at the distribution of these points vertically. And each of these have a pretty nice spread in their points. They're pretty well spread vertically. So there's no, what we would say here is there's no evidence of skewness or a wedge-shaped pattern. Again, because you have an even spread across. If you had clumping down at one end, you would say it was somewhat skewed or wedge-shaped. Okay, so since all of our assumptions seem to have been met, we can create and run the model. So we're going to run an ANOVA using the AOV function. Our response is B rating or bratting, and we're going to test for an interaction between our 2 predictor variables. This little star or multiplication symbol is used to represent that interaction term. So this model essentially will test the interaction term, but also the individual factors. And we'll pull up the summary for that. Okay, so in our output, we see that both pH or your acidity and health have p-values that are less than 0.05, which is what we're using as our confidence interval. We're using the 95% confidence interval. So since they're less than 0.05, that means the effect of each one individually is significant. So this is the effect of acidity alone and the effect of health alone. And then this is the effect of the interaction of acidity and health. And that has a p-value that is greater than 0.05. So that means the effect of the interaction between acidity and health is not significant. So another thing that I'd like to draw your attention to is that the AOV function by default gives you type 1 results, which are for fixed factors. Now there's going to be some cases where you're going to need either a model that gives you type 2 or type 3. So you can do that by using this code where you have the actual ANOVA function, your model, and then you type out this, type equals C, and then whatever type you're using. So this could be type 1, which you don't have to do again because that's default, but you can do type 2 or type 3. So we'll run that just so you can see what happens. Again, you get different results according to the type, what the type number test you're running. Okay, just so you're aware. So we're also going to look at the interaction plots. So this is made using the function interaction.plot. And based on that, we get this plot here. So looking at the interaction plot, the graph reflects similar findings to what we determined from the output of the ANOVA table. So I'm going to first explain how to interpret these plots because it seems that people get hung up on that a lot. So if the lines are parallel to one another, there is no interaction. But if the lines cross, then there is an interaction between the 2 terms, or if the 2 lines separately touch. If you have parallel lines with slopes, there is no interaction. But A has an effect and B has an effect. and you can determine that because the means change. So basically, if you have a slope, most likely one of the factors or both of the factors individually will have an effect. Parallel lines that are on top of each other means that there is no interaction. One of the terms has an effect. We could say A has an effect and B does not. So it's really hard to understand that from just me chit-chatting. So this is a wonderful little example to kind of help you visualize what I just said. So, for example, this top plot, there's no interaction because the lines do not cross. They're like right on top of each other. The effect of B, there is none, and that's because these lines. Okay, so somebody last class pointed out that there was a tiny, tiny little gap, but we're not paying attention to that. That's just separating out the two lines. But these lines are essentially on top of one another. So that means that B has no effect. But when you look at the means for A1, your mean is here. For A2, your mean is here, right up here. So because you have a change in the means for A, that means there's an effect of A. Let's look at another one. Okay, so here. So here we see, obviously, the lines are crossed. There's no disputing that. So because they're crossed, that means there is an interaction. Now, when we look at A, we can see that there is a disparity in the means. So you have when you have B on this line, the mean is down here, whereas the mean for B at A here is different. So that means there's a main effect of A, but there is no effect of B because B doesn't change. Where's another one? This one's good. Okay, so this one is just happy in every sense of the plot. So there's an interaction term because the lines touch right here. So if you extended these out, they would cross. Because this mean here at A1 is different from the mean, which would be right here for A2. Since you have that different, the difference in the means, you have an effect of A. And the same holds true for B. You go from a mean here to basically the same plot. So that means there's also an effect of B. But yeah, so if you can find something like this, it kind of helps you understand a little better if you can visualize the actual plots. So we'll go back into here. So based on all of that, we can interpret this plot. So the lines do not cross, we can see, which means there is no interaction based on what we see here. However, there's a clear effect from acidity and health because both lines have slopes and impact the mean of spruce B rating. So you can see the mean at 3 for acidity is different from the mean of 5.5 and the mean of 7. And also the actual movement of these lines change, showing or verifying that there's an effect that is felt individually for both of them. And that is crossed ANOVA.